Our goal in this section is to compute the total area under the graph of a function. Now the problem is that integrals compute signed area. For example, let's take a nice easy function like y equals 2x plus 4 on the interval -3 to 1. Plotting this out, the function dips beneath the x-axis between -3 and -2, and so has a negative area there while being positive everywhere else. When we integrate, we will add the negative area to the positive area, giving us something less than the total area. We can use the FTC to compute the signed area pretty quickly, giving an area of 8. Or, to make the negative and positive areas a bit more explicit, we can break this integral into the chunks on which it's positive and on which it's negative. The antiderivative is the same in both cases. It's x squared plus 4x. And we can work out the areas to get -1 and 9, which together give us an area of 8. And since the graph gives us a bunch of triangles, we actually could have just computed this using simple geometry. This reveals to us a few techniques for computing the absolute area. In the first case, we can compute the areas of the positive and negative portions separately. Once we know the negative area, we flip its sign and add it back to the positive area. In the example above, we would record our -1 area and convert it to a +1 area, giving us a total area of 10. Alternatively, we can change the function itself by reflecting the portion beneath the x-axis so that it gives us a positive area contribution. In the example above, we flip that negative part to make it positive while still preserving the area. Once again, this gives us a total area of 10. In practice, both techniques are pretty much identical, and I'll point this out when we do a bigger example later. However, there is a benefit to using idea number 2. That benefit is that we have a mechanism for turning negative parts of the graph into positive parts mathematically. So, we can write the total area beneath the function f on the interval ab as the integral of the absolute value of f on ab. And this is because the absolute value does exactly this process of taking things beneath the x-axis and putting them above the x-axis. So let's do a fairly involved example and find the total area beneath this function on the interval -4, 4. To deal with the absolute value, we need to know where f is positive and where f is negative. We'll start by finding the roots of f, since this is where the sign of f is most likely to change. Factoring our function as much as possible, we find that the roots are -3, 2, and 3. To keep track of this information, I'm going to use a table. And if you look at the function, you can see that it will flip signs each time it passes through a root. Alternatively, if you set the table up well, it's easy to see that you get this sort of triangular occurrence of signs. Now, while not necessary, I just want to give this quick qualitative sketch of our function. It doesn't need to be great, since we're just looking for some insight as to what f looks like. We will be splitting the integral up into each of these domains, but they'll all have the same antiderivative up to possibly a minus sign. So let's just worry about finding that now. And like I said, let's split up our integral. The benefit of doing this split is that the function doesn't change sign on each of these intervals. Thus, we can drop the absolute value, replacing it with negative f if f is negative, and positive f if f is positive. Now it's just a matter of applying the FTC to each of these integrals. And while the numbers aren't pretty, they're definitely doable. Before doing the final simplification, let me point out what I alluded to earlier about the two ways of solving this problem. If we had computed the negative integrals separately, we would have gotten these values of negative 227 over 12 and negative 11 over 12. Then we would have made them positive. But note that this is exactly what's happening here, since the double negative signs make these areas positive. Okay, and so we'll finish up and getting our total area like so. So pretty much no matter what way you decide to do this, you're going to have to break the function up into the domains where it's positive and negative. But once you've done that, you can find the total area under the graph.